Good morning, everybody. Today we will be doing our training on commercial code. We will have David Griffin presenting for us today. And with that, we will go ahead and have Dave come. Lunch will be here around 11:15, 11:30.
Hi, everybody. Dave Griffin here. Thank you for the opportunity to present today. Give you a little bit of background on me. I've been focused on energy codes for well over a decade now. I'm a past president for the local Utah ASHRAE chapter. I'm now a regional officer with ASHRAE Region 9 over technology transfer. I'm currently the AIA Utah Director at Large, sitting on their board. I'm a licensed architect. I'm certified through ASHRAE as a building energy modeling professional. I'm a Green Globes Fellow and a Living Future accredited as well. With that, some of my professional highlights is that I worked on the 19th Fully Certified Living Building Challenge project in California. It's an architectural office in Sacramento. And if you'd like to learn more about any of that certification program, we can talk later. I've also worked on 8 successful net zero projects and have a broad range of experience in the design of projects anywhere from military and federal work to warehouses and multifamily. Now you know a little bit about me. So a little bit of background for this specific presentation. It's the first time I've given this presentation. So I'm really excited about it. I think there's a lot of potential here, but I'm very open to questions during the presentation and feedback after the presentation on how it might be improved. Before we jump into the presentation itself, I'd like to thank our sponsors for funding the effort of today's training. Enbridge, formerly known as Dominion, Rocky Mountain Power, and Utah's Office of Energy Development are sponsoring this event, or supporting this event. For those of you willing to share, I would like to know what your interest is in attending today and a little bit about you as well. We've got a roaming microphone. This will help me tailor some of the content so that you get out of this presentation what you would like. Is there anybody, if you raise your hand, tell us a little bit about yourself and then what you're looking to get out of the presentation today.
So I'm Bob Coleman. I work at BYU, Brigham Young University, as a building inspector, this energy actually is interesting to me, the energy code. So, and we work striving to be as efficient as we can.
Fantastic. Thanks for sharing. Anyone else?
Keith Bennett, KCB Architecture. I'm interested in just code changes and updates as we go from 2018 to 2021, and mostly interested in multifamily.
Multifamily, okay, good to know.
Thanks, Keith. So, Keith's my architect. I'm with Ivory Commercial. So we build a bunch of multifamily locally, and we're just trying to understand what new implications that will mean for our future projects.
Sounds good. Anyone else? Okay. Well, if you change your mind or if you are in the introvert realm of things and would like to share later, feel free to do so. We are going to talk high level about general changes between previous versions of code and current versions of code. As far as multifamily is concerned, we're not going to do a deep dive today on that. We can, however, set up another presentation where we do that. I work on a lot of multifamily projects as well, especially, not just market rate, but especially low-income housing tax credit projects that require a lot of boxes to be checked for regulation reasons and funding reasons. So if you have multifamily specific questions, please feel free to ask them, even if we're not on that topic, either during the break or during the presentation. As you might know, there have been significant changes and updates to Iecc and ASHRAE from previous versions. We will be discussing some of them today. Please keep in mind the energy code is complex with many nuances, so you may not understand everything the first time you hear something, like in this presentation today, but I'll be available again to answer questions today, and you can reach out to me with questions after the class. My contact information will be on the last slide. To give you some background on that, time is limited today. The energy code used to only be 50 pages, probably 4 versions ago, and now it's over 300. So it's really hard to dive into that in a session like this. 6 hours might not even be enough for us to cover everything. It is a very complex code. Sometimes the longer you're in the industry, I mentioned I've been in it for over a decade, there are subtle nuances as well between the different versions. And as I'm in the industry longer, sometimes it's not easy to keep those nuances separated. So we'll try and do that today if need be. We can open up the different codes if there are specific questions about it. Some issues that we see in our local market, there's a low level of enforcement, unfortunately, in the energy code. A lot of that has to do with lack of training, which is why we're here today. Thank you for taking steps in the right direction to help us with that. For the review and inspection of energy code compliance is also difficult, right? So not just in the design process, but in the construction process. So again, thank you for being here today to educate yourself and raise the bar in our industry. There are some industry myths that I'd like to debunk in the commercial sector, especially. Usually code inspectors or code reviewers and inspectors just say, it's a large building. This is a really seasoned architectural firm on the project, so they know what they're doing. And if I see the CommCheck green bar, we're good to go. We're going to debunk that myth. That is not the case. In those larger firms, it can be the case, but in those larger firms, that it's been my experience, especially in the local market, that the lead architects aren't doing the CommChecks. Their interns or lower level staff are actually completing those, and they don't complete them as frequently as you might imagine, even though they're large firms. So it's good to review those, the CommChecks. And then CommCheck is not mandatory. However, it's the simplest method, and so you see it used the most across the board. There are trends in the market, though, and in energy code itself, that are leaning towards performance compliance. And we'll get into that in the presentation today. In fact, that's going to be a focus of ours today, is that performance compliance, which is so that we can help raise the bar in Utah for energy code. So on the agenda today, we're going to start with high-level information about why we have the energy code. We're going to talk about the evolution of the energy code. We're going to talk about compliance paths within the energy code. And then we're going to hit lunch. And after we come back from lunch, we're going to dive into some case studies and what the future of energy codes look like in Utah, have a Q&A session. And then, like I stated before, please don't wait until the end of the session. If you have a question, feel free to raise your hand and we'll bring a microphone to you. So to start, why the energy code? Why do we have the energy code? We're going to cover everything on this slide. I have removed some things just because we only have 3 hours and I want to get to other things. So big picture, the role of energy code. Who here is familiar with ASHRAE 90.1? versus IECC. Everybody's heard of ASHRAE 90.1. I'm seeing a lot of nodding heads, so that is a good thing. So to define energy codes set the minimum requirements for energy efficiency in buildings, covering aspects like the building envelope, mechanical systems, lighting, and electrical systems. We have energy codes because we have goals as well. There are global goals set forth by the UN for 2030. Most of the goals around energy efficiency fall in whether they're national, global, national, or local, fall in this range of from 2030 goals to 2050, if you look at that. So some of the goals are coming up pretty quick, just over 5 years for some of these UN goals. We also have national goals, which are listed here. There are trends in our industry moving towards energy efficiency, which we'll talk about here, and there are advantages to that. The biggest advantage of energy efficiency is the economic benefit, but there are other benefits of it as well, as far as better indoor air quality and other positive environmental impacts. So the economic benefits for the energy code. For those of you who were around back in 1978, energy costs were a quarter or less of what they are now. And in a capitalist society, the trend has almost never gone down, and people love to save money. That's the universal language in the US and in Utah. No matter what topic you're speaking about, everybody knows how to speak about money. So what are the other benefits of energy efficiency? There's reduced energy consumption, reduced pollution, improved public health and quality of life, national economic benefits and long-term cost savings, standardization and national consistency, energy security, and the encouragement for innovation and sustainable development. So how did we create back in 1975? How were the energy codes created? So I'd like to use Energy Star as an example. So Energy Star, in their existing buildings program, for instance, they identify underperforming buildings. Then they come up with a list of best practices, make sure that those best practices are investment worthy, that there's a good payback on them, a return on the investment. And then they go and they verify the savings to make sure that what the savings they estimated worked out, and they have a report on the performance. And with Energy Star, they were able to benchmark those the performance of those buildings with an Energy Star score of 75 being certifiable. And they look at other things besides just energy as well. They look at water, waste management, other things. And then they implement these recommendations and best practices across a portfolio. So I'm guessing, based on some of the responses that we got today, that everybody knows what an EUI is. Does anyone not know what EUI stands for? Energy use intensity. It's like a miles per gallon, but for a building, so it's energy per square foot. Helps to normalize the conditions or helps to normalize something so we can compare building to building. So imagine you're a building owner, and you have 10 stations. Say they're fire stations, I guess. And you're looking, and this is the EUI for all of those fire stations. Where do you have concerns? In this station 4 and station 8, why do you say that? Their energy, so they're performing the same function, but they're using more energy per square foot. Correct. There you go. So per Energy Star, you would their example that they use, you'd take that and you'd apply that not only to your existing buildings, but you'd also apply that those findings or those things that have worked for you in the past in new construction projects, and that's where the energy code comes in, where they've taken the lessons learned and applied it to code, whether that's building envelope, mechanical systems, lighting, electrical, and more recently, renewable energy. Oh, I've got my stuff showing up in the wrong order here. We'll just show all of it. And so the energy code really is helping to future-proof buildings. So hopefully, in the future, we're not having those outliers that are using a whole bunch of energy. We have consistency across the board, and not just here locally in Utah, but across the nation as everyone implements the same energy codes. So by doing so, we're reducing the nation and the state's dependence on energy from geopolitical powers. We're setting up the infrastructure for resiliency and workforce management across the nation as well. Those are just some of the high-level benefits of it. So this next portion, we're going to focus on a very brief history of energy code. So we talked about how it got started, why it's important, what it's doing, and sort of where it's headed. Now we're going to dive a little bit deeper into that, look at a brief history, compare those, and then talk about what's driving the changes in energy code and look at future trends. All right, so the brief history. Origins of the code, both Iecc and ASHRAE 90.1, and slight differences between them. The Iecc replaced the Model Energy Code, and it provides local jurisdictions the opportunity to adopt it to customize and promote energy efficiency, both residential and commercial. Whereas ASHRAE 90.1 was set up not by code officials, but by engineers who wanted to document best practices, and it focuses on commercial and multifamily high-rise residential, anything over 4 stories in the multifamily sector. Questions about that? No? Okay. How many in the room have seen this graph? We only got one. Okay. Well, I'll give you a moment to look at it. There's a lot that we can learn. Oh, good, it's legible too. There's a lot we can learn from this chart about the history of these two programs. I'll give you a minute to look at it, and then I'd like to get some input from you on what we can learn about the history and just in general about the differences between Iecc and 90.1. And so that I can either repeat what you say, or if you want to raise your hand and wait for the microphone to come to you, feel free to do that.
So, so the question that you asked is, what is the difference between the two? Is that?
Well, what can we learn from this graph, whether it's differences between the two codes or just in general, what we can learn about them?
Okay, all right. I misunderstood the question.
For instance, if you look at this graph, you can see that both codes run on differing timelines, but a 3-year code cycle. All right, so there's basically a highlight every 3 years, starting back around 1999. That's one thing that we can learn from this in general about the two codes. We can also see that ASHRAE has been around for over 20 years longer, that standard, than the Iecc standard. I can give you some of my thoughts, but I'd love to hear yours.
I see a lot of change between 2009 and 2012, but between 12, 15, and 18 to
Right. So there's a flattening in the curve earlier in the development, and then as we get closer to, as things progressed around the 2009 mark-ish, things started really to accelerate as far as energy efficiency. And then it flattens for IECC a little bit, and this last one, oh, just IECC, gotcha. Yeah, that's very true. I think there's a thirst for energy efficiency and it's been presented, especially more recently, as having more benefits than just economic benefits. And because it's been presented as having multifaceted benefits to the nation as a whole, more people have been behind it, supporting it for different reasons, and that has helped it progress in efficiency in these more recent years.
Would you say the HBA is a component of what kills the flat line on the IECC, since the fact that they have a big say in that code, and that, you know, sort of trajectory of which way that's going to go?
So the Home Builders Association,
Yeah.
the HBA, I can't speak to it nationally. I can only speak to it locally in Utah. And I would say that the HBA acts in not only their best interest, but what they feel is best for their members as far as energy efficiency is concerned. And in Utah, that has taken a form that you either agree with or you don't agree with, and we maybe could talk about that in the break. But for the most part, they're working towards making the building stock in the U.S. more energy efficient for some of the reasons we talked about, not just for to wean us off of our dependence on foreign energy sources, right? To stabilize our geopolitical situation, but it helps the consumer at the end of the day as well. If you're spending less money on energy, you can spend more money on other things that help the economy, our economy, which is consumer-based, really function better. There are a lot of reasons for that. It's a great question. I wish I had a little bit more insight.
How much dependence is there currently on foreign energy sources in the United States? Do you know?
I can point you to some websites where you can get the information about. I apologize. Are you on a mic in the back? Okay. So the question was if I knew how dependent we are currently on foreign energy sources. I know currently that the United States is a net exporter of energy, but that has not always been the case, nor is it guaranteed to be the case moving forward. So, but as we move closer and closer to the bottom of this chart, to zero, it helps our energy sector stabilize and stay in the position of being a net exporter. Does that answer your question?
Yes.
No problem, thank you.
Why is ASHRAE, so there's a point where ASHRAE and the IECC were pretty much tangent to each other, but the ASHRAE has moved to zero faster than the IECC. Why is that?
Yeah, great question. These are great questions. So IECC is there are different systems that are set up in order to get approval for these different changes in each of the standards. IECC has a broad range of constituents, more broad than ASHRAE does, I would say. And so although both systems follow the ANSI process, which is the American National Standards Institute, for upgrading or updating the process, there are different people at the table assisting with the update process. And so ASHRAE, because of the people at the table, they're more engineering focused. And I would say to some degree, and this is an opinion, and I'm not speaking on behalf of either organization, but because they are engineering focused, they have numbers, different set of numbers to back up what they're doing. And because they have that backup, they're more willing to adopt more aggressive energy efficiency stances, whereas IECC, which also somewhat follows ASHRAE, believe it or not, in adoption of different energy. They're just a few code cycles behind in some of the things that they adopt. They not only have engineers, but they've got code officials, developers, large building owners who are potentially a little more conservative in their approach and have a different perspective to add as that energy code becomes or evolves over time. Does that make sense? Okay. Great questions. One of the things we can learn, the next version of ASHRAE 90.1 has already been released. Just hasn't been adopted yet in most places. Let's see. And yeah, so I love this graph. There's so much we can learn from it. We've looked at this graph for over 5 minutes at least. And it's a great brief overview of the history. That's about as far as we're going to get into the history of energy code. Thank you for your questions today. I wasn't sure where to put this in the conversation, but it's very important as we talk today. And I don't know if you can see this easily, but between IECC 2018 and the 2021 version, there has been an update in climate zones based on data alone. It's really actually kind of hard to see, and so I took the liberty of making it. Oh, what happened here? There we go. Nope. There. Okay, that works. I took the liberty of blowing up the state and putting things into context. So on the right side, we have the population density in Utah. Nope, sorry, left side. And on the right side, we have the climate zones. You'll notice, if you're familiar with climate zones, that three counties in Utah changed climate zones between these latest versions. That would be Box Elder, Cache, and Carbon. Very important. They went from 6 to 5. So Logan, which high elevation, cooler temperatures, is no longer climate zone 6. It is climate zone 5. And I used Logan as an example because if you look at the density map, they're in the higher density populated portion of the state. And so for the most part, as a code official, you're going to be working in 2 climate zones based on the density in the state. You're going to be working in climate zone 3 or climate zone 5. Climate zone 6, the higher elevations that are cooler in temperature, are not as highly dense, or don't see as much construction, basically. Are there questions about that?
Why would it be less conservative as far as the climate is concerned? Why would Logan go from 6 to 5? Just because of the density?
No, it's not because of density. So that's a great question. Let me restate that for those watching virtually. So the question was, why did those counties switch over from a colder climate to a less cold climate, right? And so first we have to understand climate zones in general, right? So these maps break it down for us. I'd encourage you maybe on your own time to visit them again. There are letters after the numbers as well. So we're in climate zone 5B, right? So the letters have to do with whether it's a moist climate, a dry climate, or marine climate. And when they take into consideration what climate zone you're in, they look at a historical data set of weather over time. And so as we see fluctuations in climate, in temperatures, those the parameters with which each county meets for each climate zone have shifted. The parameters stay the same, but the data has shifted with more input. And so that's why we see the change. And the standard that regulates this is ASHRAE standard 169. The parameters within 169 did not change, just to emphasize that. It's just the data set that's evaluated for the different counties. All right, so now we're going to dive into high level some of the changes that we see. We're going to focus on ASHRAE 90.1 mainly because this is a training session and people are less familiar with it. And so let's get a little more familiar with it. You can see similar changes though in Iecc as well. So between the last version and the current version that have been adopted by the state of Utah, some of the changes are tightening in requirements for insulation in the Iecc, fenestrations, and air leakage. ASHRAE 90.1 is a little similar in envelope performance, but they also focus on thermal bridging requirements that we didn't necessarily see focused on in Iecc. As an example here, we've got windows. And I want to make sure that I'm not leaving anyone behind with the data. So I want to make sure everybody knows what, in this table, what the U stands for, and what SHGC stands for, and what VT stands for. Does everybody know what those acronyms stand for? This will be for both ASHRAE and for Iecc. I'll tell you this, most design professionals get the U wrong. So most design professionals in school that they're taught that the U in energy code stands for U value. But it doesn't stand for U value. In the energy code, it stands for U factor. Do you know what the difference between U value and U factor is? So the difference between U value and U factor is whether or not in your calculation for the thermal resistance, you incorporate the frame of the window or not. So the U value of a window takes the U value of the center of the pane of glass that you're putting on the building. The U factor takes the overall assembly of the window into account, so you're using both the glass and the frame in that calculation. That's a common mistake that design professionals make in ComCheck reports, that they'll report the wrong U factor because they'll report the U value instead of the U factor, which makes their project look better in ComCheck, right? Because the U value is lower than the U factor. Solar heat gain coefficient is a ratio of how much solar radiation is making it through the assembly. The assembly again, not just the glazing. So we're looking at the assembly. That's because frames are solid, the solar heat gain coefficient for the frame is 0. And so it's really just a ratio calculation between the solar heat gain of the glazing, or it's an area weighted average of the solar heat gain of the glazing and the frames to calculate that. And then what's new and introduced in ASHRAE is this visible transmittance of the glass over the solar heat gain coefficient, a ratio of those, to make sure that to get to the energy code requirements, you're not limiting the amount of light that's coming through the window. Because for occupant health, you want to have light come through. You just want to be able to control the interior environment versus the outdoor environment. So there's the meaning for those. So visible light transmittance is the VT, solar heat gain coefficient is SHGC, and then U is for U factor, not U value. So then we have mechanical systems. Believe it or not, it's most of the focus and efficiency updates to the codes this time around for Iecc have been in controls, not necessarily in equipment efficiencies. For some obvious reasons that if you're in the industry you would see, but if you're not, you might not see. That's because if you increase the efficiency of mechanical equipment in code, that means manufacturers have to be able to make that equipment, right? And it takes years to develop the technology that needs to go into the mechanical systems to increase their efficiency. And so on code cycles, you'll see sort of a teeter-totter sometimes where it'll be mechanical efficiency, and then they'll focus on controls, and then they'll go back to mechanical efficiency to give manufacturers time to work on making equipment more efficient. And then in the process, 90.1 has focused on some new mechanical systems that have been added, such as VRF and their efficiencies. And they've added a lot of flexibility, quite frankly, to the energy code for mechanical systems, more so than energy efficiency overall. And we see that by this example in the chart. So again, before we dive into these things, I want to explain some of the acronyms. EER is energy efficiency ratio. Good, it's large enough for you to see it. So the higher the EER, the more efficient the HVAC system. IEER is integrated energy efficiency ratio. Again, the higher the number, the more efficient the system. However, EER focuses on the mechanical equipment's efficiency at peak load, and IEER focuses on mechanical efficiency at part loads, at different part loads. BTU, this is my favorite unit of measure. Truthfully, it's so cool. BTU is basically the energy it takes to raise the temperature of 1 pound of water 1 degrees Fahrenheit. And for those of you who work on smaller systems, a BTU is about 12,000 BTUs is a ton, to kind of put that into relation so you can convert some of these numbers to tonnage. See.
8 pounds per 8 pounds per gallon. Oh, no, sorry. You said a pound of water. Okay,
A pound.
An eighth of gallons, so that's 16 ounces.
Yes. Yeah. So fluid ounces, or not fluid ounces rather, but weight ounces, if that makes sense.
You said a pound of water,
Pound of water.
but it's 16 fluid ounces.
16 ounces is a pound. Yes. Good comment. Thanks. You're keeping me on the spot on my toes. And then BTUs per hour is a power measurement. BTUs is an energy measurement. AHRI on this table as well stands for the Air Conditioning, Heating, and Refrigeration Institute. It's a trade organization that develops standards to certify performance of HVAC R and water heating equipment. The R in HVAC is refrigeration systems. So you'll see here, actually, ASHRAE between 2016 and 2019 has added flexibility in their selection for VRF systems. I chose VRF systems because it seems to be a fairly integrated system, but still kind of new. So they said, if you add heat recovery to your VRF systems, then we'll allow you to go with different efficiencies. All right, so that's the flexibility that I was talking about, where they're adding it into their mechanical systems and the required energy efficiencies. Any questions about that? Okay. Well, then let's look at lighting and electrical. So both IECC and 90.1 are gradually moving towards, actually, not necessarily keeping up in the past, with new technologies of LED lighting. So that's what I've highlighted here. They have also, though, integrated requirements for lighting controls, such as daylight controls, dimmers, occupancy sensors, to reduce that energy usage. What I'd like to point out here first, the LPD is lighting power density, so let's go through the acronyms. And then similar to EUI, which is, again, miles per gallon for energy use for an entire building, LPD is that same concept but applied to lighting. And you'll see the reductions here are pretty staggering. This example is for the building area method. So we're looking at an office building as a whole and applying this requirement to it rather than getting into the space-by-space method, which looks at individual space use requirements and dictates what LPD is allowed for those individual spaces. But you'll see there's almost a 20% and a 35% reduction in just these two categories alone. If we go back to our chart here, where we see between 2016 and 2019, the efficiency differences that were covered were it's for 90.1, it's only 4.7% overall for the entire building. Most of that 4.7% in efficiency is coming from this reduction in lighting. Is it difficult to hit with LED lighting? I'd say no. It's definitely not difficult, but if you're going for certain certification programs that go above and beyond code, it's much more difficult from lighting to prove that you're saving beyond code. So keep that in mind. A somewhat recent addition to energy code is renewable energy. Each code path that I've listed here, and we'll get into those code paths in more detail after lunch, takes a slightly different approach. So in ASHRAE 90.1, the prescriptive path, if you have renewables on your project, and depending on the project type, it allows you to take some exceptions in the energy code. And then for the performance paths, they allow you to take direct credit for them in the energy model. That is not the case for Iecc. Prescriptively, in those sections of Iecc, they allow you to take more credit prescriptively. The performance path, though, is almost exactly the same for ASHRAE 90.1. The question is, what is renewable energy? And this is a nuance that for code officials that can be really frustrating at times, right? Because I don't know that ASHRAE 90.1 actually defines what renewable energy source is. Only Iecc does in their definitions section. And so sometimes for definitions, you have to go between the two codes to figure out what they might be talking about and to interpret them. The same goes for window-to-wall ratios, for instance, in code. Iecc doesn't allow architects to to include below-grade walls in the window-to-wall ratio calculation, but 90.1 does. And so there are subtle differences between the two codes. This is just an example of one of them. Who has ideas about what renewable energy is? There are a few heavy hitters, but the list is about 8 long. Let's see how many we can get. I'm curious. What's that? We have wind and solar. Okay, that's number 1 and number 2. So we've got the 2. Hydroelectric, okay. That actually is not on the list. Buildings don't usually use hydroelectric power. Commercial buildings don't. It comes from the grid, but this is on-site generation. Geothermal, believe it or not, that is the last one on the list. So we've got the first 2 and the last one. Anybody else want to give it a try? Net zero is a byproduct of on-site renewable energy. So you're right in that regard, but it's not a renewable energy source. Okay, so we've got wave energy. Has anybody done any work in Hawaii? I mean, they've got wave energy there. We've got tidal energy, which is different from wave energy. We've got landfill gas. It is methane, but after captured can be processed into what is called biogas, which is another one, which locally Enbridge has a program for. So you can actually purchase biogas for your building. And then there's biomass as well. So those are the 8 definitions currently in Iecc for renewable energy sources. So biomass, as far as I know, at least locally, it's way more popular in Canada. So rather than burning a fossil fuel of choice, whatever that may be, for heating, they a lot of times, because lumber is a huge national product for them, they take the byproduct of that industry, which are wood pellets, and they burn those wood pellets, which are considered renewable. Yeah, and so that's a form of biomass.
Specifically wood pellets, it's not coal, charcoal?
So by definition, charcoal is coal rather is not a renewable source. Charcoal, I'd have to dive deeper to answer that one. I don't want to misspeak. But wood pellets definitely are considered a renewable source for biomass. Great question. Other questions before we move on? Okay. So again, what are driving these changes? We had a comment about net zero. So this isn't the ultimate driver. This isn't the only aspect of why these changes are coming about. In fact, I'd say it's in most circles, it's not the largest thing that's moving the needle as far as energy efficiency is concerned. But there is a push towards net zero and carbon neutrality in the building sector. There are varying definitions of what that is. There are off-the-shelf approaches and very high-tech, complex approaches to that. One of the forces that are looking to push this as part of energy efficiency upgrades is the AIA 2030 challenge, which as an architect, we have a few of those in the room, you're probably familiar with. It's a challenge that architects can sign up for, where they report in this database to the national group every project that they put through their firm and how efficient it is. And then AIA analyzes that and submits reports for it. And so the higher efficiency your projects are, the better their numbers look. And so they're trying to push architects to design more efficiently. Energy cost savings are a large portion, I would say, of what's moving the needle. But for businesses, keep in mind the scale of what we're talking about here. So for businesses, their number one largest, by far, expense are their employees. Their second largest expense is their operational costs. Okay? And there's an order of magnitude between those two of close to 10, depending on your business structure. So does it help their bottom line? Yes, in many ways. But it's also not the highest priority for a lot of businesses because of that parity. Now we could spend a whole hour talking about economics and how and we can kind of close the gap between that 10 degrees of separation, the gap between operational costs and the cost of their staff. But maybe we'll do that next time. And then one of the biggest things, because this speaks to everybody, whether you're trying to save money or be more aggressive with energy efficiency and meet AIA 2030 challenge, is health and resilience. This speaks to everyone. Everyone in this room knows someone with asthma or a medical condition that could be better if we managed our energy use in this country a little better. Our air quality gets better when we have more efficient boilers that are not impacting our air quality, when we when we look at different energy efficiency scenarios, right? I don't see in the future. I don't see the future getting better in that regard without energy efficiency. I think those two things are linked. With resilience as well, we talked about geopolitical instability. We talked about workforce innovation and helping that for resilience, not just locally here in Utah, but on a national and a worldwide scale. We see the energy codes taking this into account with ventilation and filtration requirements. And we'll talk a little bit as well later about COVID and how that impacted energy codes as well. I know it feels like, hopefully for most of us, it feels like that's distant past now. But for the code cycles that only come out every 3 years, that's still in the mix. All right, let's see here. Did it? Oh. Okay. So there are also other future trends in the energy code. So we're looking at I think this is where I'm going to talk a little bit about COVID as well. So future changes in Iecc and 90.1. I mentioned already that the next version of ASHRAE 90.1 is already out there. So we can just go and look and see what's coming down the pipe for ASHRAE 90.1. And the fact that Iecc 2024 should be released within the next 6 months, 12 months at the latest. Right, so we'll have insight into that. One of the interesting things that ASHRAE is doing right now is they're looking at adding a sixth path to code compliance, which there's a lot of debate. Again, talking about how energy code used to be like 50 pages or less, and now it's over 300 pages. How complex does it need to be in order to see efficiency happen? And is adding a sixth path appropriate? Are we making things too overly complex? But that sixth path would help employ a performance path for smaller buildings, is what they're looking at. Right now, performance path approaches have been somewhat limited to very large buildings. And so ASHRAE wants to bring that in because there is a trend towards performance path compliance in the nation. It hasn't yet really ticked up yet in Utah, but it's coming. And there's a reason for that. If you'd like to learn more about about upcoming changes in energy code, one of the ways with ASHRAE 90.1, they have a technical committee that you can join as a corresponding member. You don't have to go to any meetings. You don't have to be an expert in anything. But if you sign up as a corresponding member, then you get all the emails, so you can see all the conversations and the meeting minute notes from their conversations, so you can stay up to date on what's coming down the pipe for energy code. Similarly, ICC, the International Code Council, has a system. I'm less familiar with it though, but you can also stay up to date by going to their conferences and being a part of those meetings by volunteering. But I can tell you that future iterations will be more aggressive. It's anticipated that they will incorporate renewable energy requirements and potentially electrification requirements as well, or options at least, if not requirements. There's also been a shift to performance-based codes, which I just mentioned. The main reason is that as energy efficient code, prescriptive code, gets more and more restrictive, it also becomes less adaptable to local environment and local economics. Let me give you an example. A lab building, for instance. In lab buildings, you're required to have a certain number of air changes per hour in your building for indoor air quality purposes. And so you have a lot of exhaust, things like that. You can have upwards in some spaces of 12 air changes per hour of pure outside air. That's a lot of outside air to condition for the occupants, right? When you're changing air that frequently in a space, how important is your envelope insulation? It's not. I could show you some studies of hospital projects that we've done where the client's like, hey, we've gone over budget because of XYZ. Where can we save money? I know. You're not going to like the answer because you're a hospital and your brand, if people found out, your brand might not like it. But an answer is, hey, you don't actually have to prescriptively put this much insulation in your building. It is not helping you save money operationally because you're circling outside air so frequently. So, and we see that in hospitals, we see it in warehouses. Warehouses to, and again, this is nationwide. This isn't necessarily in Utah. The examples that I'm sharing in warehouses to lease out faster, basically to become cash positive faster. They're conditioning warehouses so they can lease space out faster. They're not just putting in swamp coolers or heating only systems. Well, when you do that, and you follow the performance path, again, you don't have to, if you put in a really efficient HVAC system, there are trade-offs you can have with your envelope that you need insulation on, but we've all seen the diminishing returns curve of insulation. The more insulation you put in, the more the diminishing returns are for the cost of that insulation. So the difference between R25 and R30 in your roof could, in some warehouses, is like the difference between $100 to $200 in operational costs a year. But first costs, that's a difference of over $100,000 in first costs. And so we've seen a push to save on first costs going towards the performance path. That's one of the trends and some examples of that shift. Again, because the prescriptive path is becoming less and less flexible to the local environment. Other future trends, let's see. So just to be aware, Utah, it's actually a much more simple process because there's a statewide energy code, statewide building code. In other states, they don't have a statewide building code, so every municipality and county has their own adoption rate of different codes as they come out, and they have amendments. If you do any work in the residential sector that's not multifamily, on single family or low-rise multifamily, you know there are a lot of amendments to the energy code in the state of Utah. Thankfully, in the state of Utah, for the commercial side of things, there's only one amendment right now. And it changes the mandatory requirement to have plug load controls in your building to be optional. And I've talked with state code officials and some of our legislatures, and although they've left out specifically in the language of that amendment, ASHRAE 90.1, that optional requirement extends to ASHRAE 90.1, which also has a mandatory requirement for plug load controls in commercial buildings. In multifamily projects, that really only applies to your common areas, like your offices, things like that, not your dwelling units. So because of that, we see future energy codes allow for local adaptation, shifting from prescriptive more so over to performance, to make sure that they're effective. Let's see, how am I doing on time? Are we gonna? Okay, who's hungry? All right, I think I was hoping to get through this next section before lunch, but that's okay. We'll just speed up a little bit more. Are there any questions about the what we've covered thus far? Okay. I'm available during break for side conversations, and again, at the end of the presentation today, my contact information will be there, so we can have that. For now, I think we should break for lunch. All right, thanks everybody. I hope you had a great lunch and you're rejuvenated and ready to dive into things. Lunch was really good. I hope you didn't have too much and you are sleepy and ready for a nap. If you are, though, that's okay because we're going to be really engaged even more in this next portion. We'll jump through the overview of Energy Code compliance paths fairly quick because I'd like to actually jump out of PowerPoint and get some eyes on to give you some exposure to other energy-related things when it comes to the performance path. So we'll talk about all 5 paths and in this next section and why you might choose one over the other. Let's see here. Okay, so, I'm supposed to ask you, who knows all 5 paths that you can take? I'll back up so you can't see. I did give you a hint, so if you were not falling asleep, you might have an idea. And does anyone want to guess? Okay. Yeah, we'll just go with it. It's okay. So there are 2 paths within Iecc for Energy Code compliance, and there are 3 paths within ASHRAE 90.1 in order to comply. Now, why are we talking about both of these? I mean, didn't the state uses Iecc building codes? What does ASHRAE have to do with this, you might be asking? Well, there is a section in the Iecc that states you can either comply with Iecc or you can comply with ASHRAE, the corresponding version of ASHRAE 90.1. And because of that phrase in Iecc, we get to talk about ASHRAE 90.1 as well. It is important to note, though, that it, and very specifically in Iecc, it states that you can do one or the other. You cannot mix and match. Okay? So whichever one of these 5 paths you choose, that is the path you take. You can't just choose whatever you want. And so, let's see, in Iecc, if you looked at section C401.2.1, that's the section that talks about both the prescriptive and the performance path. And again, I mentioned or no mixing. Based on section C402.2.2, you can choose the corresponding version of ASHRAE 90.1. Now, I say the corresponding version of ASHRAE 90.1 because it doesn't state specifically what year of ASHRAE 90.1 you have to comply with in Iecc, but the intention is that you comply with the corresponding version or most recent version of ASHRAE 90.1. So both prescriptive paths for both Iecc and ASHRAE 90.1 are included in ComCheck. If you're not familiar with ComCheck, we'll introduce you briefly to that. And then the other 3 versions require, on the performance path, require some form of an energy model. The two paths that require an energy model in ASHRAE 90.1 have slightly different perspectives, I guess you could say, or takes on it. We'll talk about what those 2 differences are. The first one is follows section 11 of 90.1, which is generally referred to as the energy cost budget method. The second follows the Appendix G version of ASHRAE 90.1, which is generally referred to as the performance rating method, or PRM. Questions about that? Okay. Let's see here. So who doesn't know what ComCheck is? Okay. Everybody here, no one's shy. Everybody knows what ComCheck is. Okay, I've got one head that's shaking no. So just in case there's somebody else who just doesn't feel like speaking up, we'll go over that. So ComCheck is a simplified way of documenting energy code compliance prescriptively. Okay, I'm going to jump quickly, hopefully, out of PowerPoint and go to ComCheck. It used to be that there were different versions of ComCheck. You would download them or install them on your computer and then be able to use those versions. They've gone away with that completely. Now the interface is 100% via their website. This is their website. So when you start on ComCheck, you'd want to create an account to log in. I'm going to log in real quick to show you the process. To start, you'll put in some project information. Some of the most important are up here in the upper left. So you want to put Utah as the state because it will go and draw on Utah amendments to code. It's smart enough to know what those amendments are, and they've incorporated them into the software. And then you can pick the city. You want to put the city in there so it knows what climate zone you're in. So we pick a city. And then I wish, and previous versions had done so, I wish that based on the state and city selections, it would limit the amount of selections you could make in this code that you'd like to follow, but it doesn't currently. And so we know that we can choose 2021 IECC, or we can go with ASHRAE 90.1 standard for 2019. We can choose either of those paths. Again, ComCheck will prevent you from mixing those two codes. You select which one you want. And then if it's new construction, an addition, or an alteration project, it's important to understand the definition of what a major renovation is to figure out whether you're a newly constructed project or not, or an alteration project. And you're off to the races. Once those things are filled in, you have a compliance path for air barrier. Usually projects choose the assembly or air barrier permeability. Most projects do not do the air leakage test for cost purposes mostly. Questions about that? It's simple. It's straightforward. And it produces all of the documentation that you need to submit for permit. It submits, or it creates all the documents that you need as a code official to inspect the project. It is wonderful in that regard because it's streamlined, it's simple, and you'll get the reports, inspection reports and mandatory requirements, those sorts of things for 4 categories, basically envelope, the lighting, mechanical systems. I provided a link to the webpage that we were just at so that you can go and get more familiar with it. It's really nice software as well because the help feature is in the program. You don't have to leave the program. It defines everything for you if you have questions about it. It's a very well composed approach to or tool to use for code compliance. But there's a trend away from prescriptive compliance. And that trend, we're going to focus on 90.1 for the purposes of this rather than IECC, mainly because, if anyone knows of anything out there that's available, please let me know because I'm unaware. The performance path for IECC does not provide design professionals or code officials or inspectors with a standard way of determining compliance and listing inspection requirements, that sort of thing. They're very general in IECC on the performance path, and as far as the searching that I can find, they just don't provide the documentation for it. My guess is because up until now, most people haven't been going the performance path, or if they have, they've been choosing to go with the 90.1 version rather than IECC anyway, so they haven't put the effort behind it. But if I'm wrong, please feel free to correct me either online in the comments or today during the presentation or at break. So ASHRAE 90.1 does now provide a very streamlined approach to it, to both the ECB, which is the Energy Cost Budget Method, or Section 11, which was mentioned earlier, and the Performance Rating Method, or Appendix G method, via a spreadsheet. The spreadsheets that, as code officials and design professionals, that really you focus on are the Dashboard tab and the Energy Performance Summary. Let me show you what it looks like, so that in the future, if you ever see it, you will not shy away from it. You'll know what to expect. I have gone ahead to avoid any technical issues and downloaded the file. You can download it from the ASHRAE website. It is publicly available. You do not have to pay for it. In the past, ASHRAE has and ASHRAE standards have been something you've had to pay for in order to get access to. That is not the case anymore, mainly because so many jurisdictions, public jurisdictions, require it, and because there was a court case about it actually, because public institutions require it as a standard, ASHRAE could not sell it to profit on it, because it was a public standard. So those public institutions had to provide access to the standard for free. So if it is a standard with the county, with the state, with the city, you can find access to it for free. You do not have to pay for it. This is what the interface looks like. Engineers are generally fairly okay with this interface because they work and live in spreadsheets for the most part. At least at some point in their career they did. It is a little more cumbersome than ComCheck is, and a lot more distracting than ComCheck is. ComCheck only puts in front of you what you need to know. The helps are integrated very seamlessly into the software. Here, you have to read the help and go back and forth between tabs to try and figure out a lot of times what you're doing. They do give you instructions. A lot of the instructions are for the energy modeler themselves and for the design team, not for code officials. They give you an overview. This is very nice. So you'll see that these names correspond with tabs in the workbook. And so these initial tabs will be filled out by whoever is contractually obligated to do so, usually the energy modeler, but it could be anybody on the design team. Some of the information that's required is not included in the design documents for the energy model, such as the energy source, electric, gas, utility rates that are associated with any of those energy sources. And those are just a couple to name some examples. Operating schedules are important in an energy model. In prescriptive, they're not. So you get used to dealing with reaching out to owner groups and figuring out how the building's actually going to be operated, or at least how it's intended to operate, whether it's going to operate that way or not. Sometimes, depending on how sophisticated the client is or the owner is, you get varying levels of confidence in how the building will be operated. The meat of the documentation for most people comes from the design documents. So the design documents, you feed into the envelope tab, the lighting tab, HVAC, service water heating, plug and process loads, and renewable energy. All of that information should be on the design documents. If it's not on the design documents, then whoever is in charge of code compliance should make sure that it gets added to it. And then all of that information up to this point it feeds into the energy model. and the energy model works its magic with all the algorithms input into it, and then it feeds back potentially into certain categories. I don't know why they didn't put an up arrow here into the envelope and service hot water and things like that, because and we'll talk about this in examples, where energy modeling can be used as a cyclical process. If you run the energy model and your project is not code compliant, guess what? You have to go back and change something. And when you change something, then that changes the output for the energy model. And so it's a cyclical process that occurs until you find a solution that works for all the priorities you're balancing on the project, whether that's energy, usually it's energy compliance or a third-party certification system, or both, and first costs or return on investment, which is, or all of them. There are many different priorities that you can have, as I'm sure some of you are familiar with. And then as we get over here to the end, there are exceptional calculations. So we'll talk about the different energy modeling software that are out there that are fairly typical. None of them are perfect. So depending on the questions that you're trying to answer with the energy model, you choose the appropriate software. Though each software is not necessarily particularly suited for every situation. And so there's what's called exceptional calculations. So if the energy modeling software is unable to model a portion of the energy code, or the energy model, or the HVAC system, for instance, is not typical, so it's not included in the energy code, there are exceptional calculations that would be submitted to the jurisdiction having authority, explaining how the energy modeler, energy consultant, energy engineer made calculations either outside of the energy model and post-processed the results, or did some fancy gymnastics within the energy model to properly or appropriately estimate the thermal dynamics that would be experienced in real life, so that they're very transparent about their process. Okay. And then in the workbook as well, there's you upload the results from the energy model, and there's a quality control component to the workbook as well to help make sure that that code officials, when they're reviewing it, don't have to make the same comments over and over and over again. And finally, what's nice about this as well, and not necessarily accessible via previous versions of documentation for Performance Path, they give you printouts similar to ComCheck of all the required inspections and mandatory provisions that have to be inspected and by code officials. It's very nice this is very nice, and I'll show you a version of what was previously used, and you'll be very appreciative of this. Similar to ComCheck, there are inputs. This software or file covers many different things, like the Energy Star multifamily new construction. I think it's because this product comes from from PNNL, the Pacific Northwest National Lab, and they've been contracted to not only provide this form of documentation for 90.1 performance paths, but also for these other programs, and so they just include it all in one tool. But for today, we are going to use 90.1. And when you do that, then it allows you to select different versions. Again, this is used across the country. Not everyone is as quick to adopt versions of the energy code as Utah is. So we're currently at 2019. 2022, as we talked about earlier, is already out, but not adopted by Utah yet. And then there's 2016 is available as well. So you go through this and input all of the things that you need to input to be transparent about the energy modeling process. And then at the end of the day, there's a lot more information that gets put into this than there is in ComCheck. At the end of the day, then you get to come over here all the way to the end. and you get an energy performance summary. That's what will be submitted for permit to the code reviewer. Unlike in ComCheck, there's not a green bar or a red bar that tells you whether it complies. So that's unfortunate. But it also then requires you to kind of know what you're looking at and to educate yourself so that you can walk through this and put your stamp of approval on it as the jurisdiction having authority. There's also a way to track revisions based on back and forth from the code reviewer, design team members, however you want to use it. And then this is where you, where are the buttons at? Somewhere in this document is very big. Somewhere in this document, there are buttons that you push, and based on the inputs, it creates the inspection reports. So I apologize. There's always a chance when you do things live that you're not going to be able to find things that like you like. But that's the interface that's been provided for 90.1 compliance. As far as I know, there's not an interface for IECC's performance compliance. Questions about that? Okay, we're going to jump back into the PowerPoint then. I provided a link as well where you can go to download that file for free. All right. Oh, this is fun. I kind of already covered this. But why do you think that this slide is blank? So I kind of ruined it. So it's basically like IECC performance path. There's like no way to document it. So I thought I'd throw that in there just for fun. I'm getting a few chuckles. That's good. My jokes usually land pretty flat, so I'm glad that one was good. Okay, so let's look at these 5 different paths in a little bit more detail. So IECC prescriptive path, it sounds like most people in the room at least are familiar with it. It's straightforward. There are itemized requirements that walk you through everything from envelope, HVAC equipment, water heating, lighting, plug loads, renewable energy, and each element must meet a specific standard. It's used a lot on small and medium commercial projects that are straightforward design. Examples would be retail stores, warehouses, small office buildings. What are the advantages of it? Ease of compliance. The checklist approach makes it easy for design teams to follow. It makes it easy for inspectors to follow. We'll cover that in disadvantages. So it's generally cost effective. It takes a lot less time prescriptively to comply with code. And then there are lower review times, right? Because people are more familiar with it and it's a check the box kind of approach, it just takes less time to complete the review. However, there are disadvantages. One is that the requirements prescriptively can be quite rigid in some cases. Right? You either test and seal your ductwork, or you don't. If you don't, you don't comply with prescriptive measures in IECC, for instance. And then, because there are complex projects, there are cases, even though the energy code has gone from like 50 to 300 pages-ish, there are still cases out there that just don't fit in the box for the energy code. And when that happens, it doesn't really flex to allow those. And a lot of that complexity comes into play on larger projects, or where third-party certifications are also being considered. So the IECC performance path, what is it? It allows for whole building energy performance. It's a lot of flexibility. And it requires a baseline model and a proposed model. You'll hear those terms used often when you go down the performance path. So the baseline model is the code required baseline. So whoever builds the energy model will build the designed building in an energy modeling software with all the different performance criteria that's required. And then when they're done with that, they'll take and they'll change all the inputs to meet the baseline requirements for the performance path, whether that's the energy code or energy, the performance rating method or the energy cost budget method within ASHRAE. They have different baselines. For instance, ASHRAE 90.1 2019, the biggest difference is that the baseline for Appendix G is actually the energy code from ASHRAE 90.1 2004. Believe it or not. And we'll jump into why they do that or how they make that possible. Like, why would you have the baseline energy model be something from a decade ago, where when we looked at that line chart a decade ago, it was way less efficient? Why would you do that? So we'll talk about that a little bit. The energy cost budget method takes a different approach. What it does, instead of taking the baseline back to a certain point in time, it says for the baseline model, you're going to hold certain things neutral. For instance, fan energy or fan power, so kW per CFM, or pump energy or watts per GPM, for instance. You're going to hold that constant in your proposed and your baseline model. So then you're only looking at very specific components of the building and how they affect your compliance. So those are very different. The other big difference in 2019 version is the building performance factor, which we'll cover a little later in the presentation. So when is it appropriate to use this performance path? When there's design innovation, when there's a complex layout, when there are high performance goals. Sometimes this performance path is chosen just because there's already an energy model for other reasons on the project. So why not free up some time for the design team and just cost effectively put that on in the scope of the energy engineer? Has anybody worked on a project in the room that's taken the performance path? I'm curious. Either Iecc or 90.1. So this is pretty new territory then, it sounds like, for most people. Okay, so the advantages, again, design flexibility. It encourages higher efficiency in design in some ways, but it also allows for trade-offs in the design, which can help with first costs. And it helps to optimize sustainability goals that might go above and beyond code compliance. Disadvantages. There's a higher compliance cost. Now, instead of having this streamlined process that most people are familiar with, you're using a process that less people are familiar with, and you're bringing potentially a new consultant on that has to be entered into the communication and coordination effort for the project. And there's a more detailed verification process, right? I know this oversimplifies things, but I've mentioned it before with ComCheck. A lot of times, if at the end of the day you have a green bar on ComCheck, you're going to sail through code review, permit review, and the design team loves that, and then the inspections are on the contractor kind of thing. With this, you saw the workbook. There are a lot of inputs that have to be put into that. There are a lot of I's that needs to be dotted, a lot of T's that need to be crossed, and it takes training for the code official. It takes the code official more time. It takes everybody more time on the process. So then there are similar paths in ASHRAE. Again, you have to separate the two completely. You either go IECC or you go 90.1. In 90.1, the biggest difference is that it's well suited for projects with designs that can meet ASHRAE's more stringent commercial standards without substantial customization. Now, I tried to be as non-biased with the information provided in these. So this, I looked for sources nationally, not just in my head, for what I would say were good. So when I say that ASHRAE is more stringent in their commercial standards, that is based on the line chart that we looked at earlier, reflected in that. Like they're just more efficient. They do it in different ways though, and so more stringent is relative. I don't want to. I don't want anybody to start a fight with me over that or a long discussion. So we're going to move on from that. And then the performance paths are the benefit, or the compliance paths are similar as IECC, but they are actually more rigorous, right? Because IECC doesn't see the performance path chosen very much within their standard, they haven't built that out as much. They rely more on ASHRAE, or expect more people to use ASHRAE 90.1 for it. And so we have these two paths. I've already talked about the differences between the two paths. The one interesting thing that they look at costs for compliance, not necessarily energy itself. And so within energy modeling, there is a term that's called fuel switching, where in the baseline model, you'll have different fuels for your building than in your proposed model. And because the standards are based on cost, it's advantageous, for instance, to have electric heating in your baseline model, which is more expensive, and then have gas heating in your proposed model, which is less expensive. I'm not going to go into detail about that today, but you should be aware of it because it is something that can occur. Let's see here. Okay. So there is something as well in the performance rating method that they call the building performance factor. So ASHRAE is trying to make it easier, for once, not harder, to understand and comply with energy code on the performance path. And so what they've done is they've taken a point in time and in energy efficiency, and they've set it. They said, this is not going to change in our standard. So on the performance rating method, the baseline year for the energy model will always be 2004, is what they're saying. And then what they do on top of that is they say, okay, take your baseline model from 2004 requirements, apply this building performance factor to the results based on your climate, the climate that you're in, and the use of your building. I've listed some building area types here and the climate zones applicable to Utah. And instead of updating the baseline model every year for the energy code, they'll just adjust these building performance factors to make the buildings more energy efficient. Does that make sense? And so you'll see here, I did similarly with the other slides. I've shown the 2016 values and the 2019 values for ASHRAE 90.1. And you can see the general trend is that the building performance factor decreases, which means your baseline energy model will be more and more efficient over time, is basically what that means. And this may be somewhat of an oversimplification, but it's basically X plus your building times your building performance factor equals Y, where X is your baseline energy consumption, Y is the building performance factor, and then Y is the actual result that you're going to compare your proposed model performance to. Questions about that? It's fairly simple. I think in a way ASHRAE has simplified the process. This has made it much more difficult to comply with the code in some instances for different building types. I think more rigor could have gone into choosing the numbers to reduce the baseline by, based on climate zone and building type, than ASHRAE put into this effort. For that reason, not every project chooses to go the PRM method because of this new performance building factor. This is new. I think they introduced this in the 2016 version. This is the first time that it was seen in ASHRAE 90.1. So this is the second iteration. They have the third iteration of it out. But we've run across projects that just prescriptively comply, but performance, during the performance pass, they just don't because of these building performance factors. But when you choose to go, sorry, let me go back. Oh, I think we're going to stick with the performance rating method for now. So similar to the IECC path choosing performance, you have the similar benefits for ASHRAE 90.1. You choose it based on project complexity, based on energy and financial goals for the project. Again, ASHRAE focuses on dollars rather than just on energy. You would also choose this based on budget and time constraints, right? So prescriptive is more streamlined. There's less time put into it. Time is money. And then not only is time money, but because it takes more time, then your budget or your project schedule might have to be extended. Hopefully not, but might have to be extended based on the energy modeling effort. And then based on market requirements as well, you might choose this path. If the building or project is already using an energy model for green rating systems such as LEED or Energy Star, or has other net zero aspirations, then it allows flexibility in code compliance for that as well, and doesn't necessarily add more budget or more time to the project. And that's what we were supposed to talk about before lunch. So let's dive in to energy modeling itself. So we've talked about energy modeling. Who here has actually seen an energy model? Has anyone seen? A few people, okay, but most of you haven't. I'll show you what one looks like as I accidentally open up way too much stuff. Oh, I wish. That was so nice and organized. Let's close out of that. So one of the softwares, excuse me. One of the software tools that we'll talk about later is Iecc. It's been around for a long time. We'll talk about its advantages and stuff later. This is the interface for it. And we'll go open up a file. So contrary to everything that I've been talking about today where energy modeling makes sense for large projects, this is actually a small project. It is less than 20,000 square feet, and it is in Utah. You can see it takes a while to open. It's really old school. The graphic interface is just wonderful, right? You can tell that that an engineer like the one who made that spreadsheet, that was an amazing, worked on this software. Okay, so you open it up. This is the building in 2D. It's a one-level building. All the boxes that you see are thermal zones, which would come from your your mechanical engineer. This particular software highlights which spaces have daylight controls in them. And then you can also do glare analysis, which this project did not have. So if the arrows were pointing towards the window, you could do some glare analysis as well as have daylight controls. This is the beautiful 3D view. For you architects out there, I know that this just makes you cringe. But to an energy modeler, this is like, wow, somebody did a good job on this energy model. So it's colored by things that affect the thermal performance of the project. So windows are here. The walls are colored by construction type. The roof is also a different construction type. And then the beautiful overhangs that the architect designs that are amazing are diminished by these black shades here. And you can have doors as well. So doors is another construction type. Some of these are overhead doors. Some are what are referred to as man doors. If there were skylights, you'd see skylights on here. We aren't going to spend a lot of time on here. But the reason why the spreadsheet had so many inputs to it, based, or at least a lot more compared to CommCheck, is because of the number of inputs that go into this. Okay, and so there's an interface that goes into all of this. Let's see if I can go. So it's basically a glorified spreadsheet. And Iecc is known for having a good user interface compared to most energy modeling software. At least in its heyday, it did. And so you can see this is just plug load inputs for each of those thermal zones. So it can get quite complex really fast. And with any type of software, it is garbage in, garbage out, which is why there is a rigorous QA/QC process for this built into the compliance inputs. Questions about that? No? Okay. Well, now you can say you've seen an energy model. Okay. Some of the energy models don't have a 3D interface like that. They're text-based. So you go into Notepad or something similar, and you type in everything that you need for the building, all the geometry, everything, and then you press a button and it runs the energy model. There's no 3D interface. There's nothing, and it's not fun. So, sorry. So you get done with all those inputs. You run the model, which takes about as much time as it does to open the model. What's nice about an energy model, though, as well, is that you can compare different scenarios. And we'll get into examples of how you might compare those different scenarios to for code compliance or for other reasons. Why is the performance path important for compliance? Again, we've talked about this. It's less important for compliance as far as complexity, because again, the thicker energy code gets, the more scenarios that the prescriptive compliance covers. That's why it keeps getting thicker and thicker, because it wants to cover every different scenario and introduce more requirements for energy efficiency. But there's flexibility, and then there's energy savings. So rather than just checking a box, you can confirm that the things that the owner of that building is investing in are going to save them money over time, and it becomes an investment rather than just checking a box to get the building up and operating. Oh, I'm glad that I'm repeating some of this information so that we can move on to get further into the presentation. Okay. So projects using the performance path are complex again. What's nice about that's mentioned on this slide that we haven't mentioned before is if there are renewables on the project, you can use the energy model to help size the renewable energy on the project to make sure that it's right sized for your goals and your energy consumption on the project. Some owners just prefer energy modeling over compliance because it allows them to look at the return on their investment. Some owners, especially large building owners in the state of Utah, I guess the largest building owners are Intermountain Healthcare, the state of Utah itself, and the Church of Jesus Christ of Latter-day Saints probably are the largest ones. So, because they have such large portfolios and they're investing in their buildings so often, it makes sense for them to invest on the front side to know how their money is going to return for them on their investment. You can do simple payback analysis with the prescriptive path, but return on investment analysis and life cycle cost analysis, you really need you need an energy model for that type of investment grade analysis. So let's see. Energy models, we talked about non-traditional systems. What can you think of any non-traditional systems that might be used that would not fit under the prescriptive path? What's that? Fireplaces, I'm not, usually fireplaces are on the residential side, which I'm not an expert on. I don't know actually that traditional fireplaces are even allowed in new construction on the residential side anymore because of the air quality that we have. That's mostly driven not necessarily by local desires, but by federal regulation from the EPA. Some people are getting pretty creative. During the break, we were talking about how some larger institutions are using they have, for instance, they have a campus of buildings, like higher education, BYU, for instance, or the University of Utah, or you name it. They've got a central plant, and what they're doing is they're with the increased popularity of VRF and water source heat pumps, they're tapping into their chill water return to their central plant and using that for some of their base load. That's a scenario that's not prescriptively covered necessarily by the energy code, but it has a lot of advantages. As long as you're not heating up your return water too much, or since you're on a loop, you're not heating it up too much for the buildings that might use it that are further down on the loop in its progression, right? So effectively what they're doing, though, is they're using that energy that is considered a renewable energy by definition to condition their buildings. And what they're doing as well back at the central plant is they're increasing the delta T that their chiller sees, so it performs higher on its performance curve. So there are some technicalities you have to work through, but it's very technical. But the benefits outweigh the issues that you have to work through to make that happen. So you need an energy model to kind of figure out how to operate that and what benefits they're going to have versus any disadvantages. Let's see. We already talked about LEED. What are some? Are you familiar with other third-party certifications? I think someone, at least during the break, had mentioned Enterprise Green as a third-party certification for multifamily projects in the residential side of things. LEED was the first one to the market with a third-party certification for buildings, so they have a lion's share of the market still. But is anybody aware of other third-party certifications?
NGBS one?
NGBS. What does that stand for?
That's LEED's new name, National Green Building Standard.
Oh, so NGBS, the National Green Building Standard, is affiliated with LEED, it sounds like. I'm less familiar with it. There's GBI, the Green Building Initiative, which runs the Green Globes certification. There's ILFI, or the International Living Future Institute, which is a mouthful. I think they're trying to rebrand that now. But they have several certifications from the Living Building Challenge down to, I don't know, all these organizations have a suite of certifications you can go through. I think LEED, their parent organization, USGBC, the United States Green Building Council, has WELL certification. They have what's called site certification, and all of them are acronyms, and all of them focus on different aspects of the project, the building, and the project's design. All of them have a new construction or an existing building component to them as well, or most of them do. Just to name a few. So there are a lot out there. All right. So let's talk about the energy modeling process, which we haven't talked about much. The spreadsheet that we looked at covered it high level. Let's go into a little bit more detail. So one of the first steps when building an energy model is data collection. Okay. And this is an ongoing process throughout the design process, and can be actually after occupancy as well. So some of the things that you're going to want to know. You're going to want to know how the building operates. Again, we talked about schedules. Usually you want to focus on occupancy schedules, and most other schedules follow the occupancy of the building. All right, so you're going to start turning your fans on an hour before people show up. You're going to turn them off an hour potentially or so after people leave for a typical office building. Your lighting schedule follows occupancy. Your plug load schedules follow occupancy. Temperature schedules follow occupancy, outside air flows, and minimums follow occupancy for the most part. So when you're dealing with an energy modeler, you want to start generally with the occupancy schedule and talk about that, and then most other things fall into place based on that. There is a website out there called ComNet, which focuses on this. So it provides you, based on your building type, with some standard operating schedules. So if you're less familiar with the energy modeling process, that's a good place to start. It's not perfect. The schedules are fairly good based on the building types, but some of the loads are not, the unregulated loads are not necessarily appropriate. So for like plug loads, that's considered an unregulated load in an energy model, because code doesn't require you to hit a certain threshold, whereas lighting is a regulated load because they do. HVAC system specifications. What type of system? Generally, you not only want to know what type of system, you want to know how many zones are going to be, thermal zones are going to be in the model. You want to know what basis of design equipment is from your mechanical engineer. They don't have to have the system selections done, but they need to have some basis of design equipment types that they can feed to the energy modeler. Envelope components. You don't necessarily have to have the assemblies, but you want to know their thermal performance. For windows, for doors, for walls, what insulation is going to be in them. And then we talked about lighting and plug loads as well. Generally, at the beginning of the design process, you don't have lighting power densities for the proposed design, and so you target a percent better than what code requires, whether that's 20% or 10%, so that you have leeway in other areas or trade-offs, potential for trade-offs. You'll need, like I already mentioned, occupancy and use, and then the climate zone information as well. If you're interested in financial performance, you'll also want utility rates. So once you have, okay. So the next thing after you have all the information you have, and it can be a process, you can start building the energy model without having all the information. You ask yourself what answers you want the energy model to give you, and based on that, you choose the software you want to use. And then once you have the software, you start building the building, and you calibrate the energy model as well. By calibrate, you can calibrate it to many different things. Calibration generally in energy modeling is when you're working with an existing building. You calibrate the energy model to an existing building, and then when you renovate it, you update the model to the renovation status or the efficiency and look and compare those. But calibration can also be as making adjustments to the energy model as the design changes and as the program for the spaces may change and be moved around. So it's a continual updating process. And there should be a QA, QC process internal to the energy modeling team set up. Once the model's ready to go, then you can run it. You can run it once. You can run it 100,000 times once it's set up. So you can look at a lot of different things and look at a lot of different scenarios. Based on energy modeling outputs, you might be interested in simple payback. For financials, you might be more sophisticated. I'm a proponent of life cycle cost analysis rather than simple payback, which looks at the overall life cycle of the building and whether or not that efficiency upgrade or code compliant approach is going to pay back over the life of the building, or when it starts to pay back over the life of the building. It takes into account maintenance costs and timelines, residual costs, salvage costs, or not, those aren't costs, but well, it takes into salvage of the material, the benefit of salvaging it, whether you're just recycling it with residual costs or if you're salvaging it for parts and using it elsewhere. It also takes into account inflation over time. And so an owner can look at, well, if I invest in a more efficient chiller today, is it better for me to do that, or should I just go to the stock market and put my money there? What's going to give me the better payback? So it looks at that as well. And then step 4 is to evaluate the results. I want to show you something that I wish we had a live example of, but we don't. We tried to set this up, and for some reason, there's a firewall on campus that's preventing me from accessing. Why is it not opening? Preventing me from accessing this particular website or app that allows it to be live. So let's go to presentation folder again and look at, where are you? Nope. Nope. I already have it open. Look at that. It didn't make it into my folder, so I'm glad I had it open. So when I mentioned that an energy model can be run once or it can be run 100,000 times, I meant it. And there's not much added effort to run it that many times. And when you do that, you can look at things differently to balance code compliance and other things on the project. Some modelers take this approach, some don't. This particular project is in Utah, and the model was run, I think, 12,000-ish times. And what they did, on the left side of the graph, you have the energy modeling inputs, all that data collection that occurred. And in this case, they wanted to look at from left to right, slab edge insulation, building envelope infiltration, lighting power, equipment power density, different lighting or different glass types, window frame types, even HVAC systems, and what utility rates they might be using. And then on the right side, where you see all these different lines diverge, those are energy model outputs. Okay, those are results from the energy model that you can that you can look at. Now, generally with this data set, you'd be able to apply filters live and look at the results. So some of the outcomes that the client was interested in this case were electric costs, gas costs, and total utility costs. They looked at EUI. They were going after lead. So they wanted to look at how many lead points they could potentially get. They wanted to also look at any additional first costs and lifecycle cost savings. We use lifecycle cost savings because it's usually a much smaller number than lifecycle costs. And so it's just easier to fit on the graph, quite frankly, and easier to understand, to see the delta. Now, when I say filtering, this is an example of that same data set being filtered with the results. So this client was really interested in focusing on, for instance, in one case, the 40-year life cycle savings. So over on the right side, we filtered in all the solutions that had a positive life cycle savings. Okay, so anything that's not life cycle effective are removed from the chart. And when we do that, you can see that there are certain outcomes. So some of the HVAC system types are no longer in the data set. So only option 2 and option 1, if the owner is looking for outcomes that meet this criteria, can be selected for the project. You'll also see that something that the performance of the project is dependent on, but is not regulated by code or necessarily by the owner, is the equipment power density. Right? And in this case, the owner wanted to be conservative and say, we want to make sure that even if we have a million cell phones plugged in and charging, and people are cranking our servers and using our Wi-Fi all the time with those plug loads, that we're still going to have a good return on our investment. You'll also see that that when they look at positive life cycle savings results, that there's minimal first cost, which is nice, but their sustainable goals kind of plummet. Instead of getting a whole bunch of lead points, they only get a few lead points, 6 or so is the most they would get. And their EUI is much higher as well. So an energy model helps you balance these results. I wouldn't use the word optimize. I would use the word latitude, right? I don't think an energy model is going to optimize anything for you, but what it can do is it can show you where in the design and in the building you have latitude based on the results that you want to, based on the outcome that you want to have. For instance, if your goal was to have positive life cycle savings on this project, well, look where you have latitude to make decisions. It says on the HVAC systems, you don't have much latitude. You have to choose either option 1 or option 2. But when you look at the envelope options that are left on the table, this particular project says you have a lot of latitude with your envelope design to meet the financial criteria that you have. All right, so you're not necessarily optimizing with this approach, but you are looking at where you have latitude in the design. Questions about that? Does this look like your grandma's macrame or something? I don't know. Just, yeah, it kind of does. Okay, so that basically covered everything that I wanted to talk about on this slide, right? So we covered how you compare the results to code and to other outcomes. We talked about modeling optimization or looking for where there's latitude. Yes. I'm now going to actually present my screen for those of you online who didn't hear that. Thank you for that comment. And then we also talked about different performance targets other than just code. Some of those targets are set by Utah's high performance building standard. Some are set by green building certifications. Others are tax incentives, utility incentives, so on and so forth. So let's talk about the options you have for energy modeling. Some might say who live in the world of energy modeling that energy modeling software is a dime a dozen. There's always a new one popping up every year, it seems like. But I've included most of the ones that have endured the test of time and that have the largest market share here. Equest is a great software. That's the one we looked at. However, it's no longer supported, and its development team, I think, is really over the retirement age at this point. I don't know that they have a succession plan in place. So it's great, especially for existing buildings that have VAV systems and older systems that it was tailored for. But unless you're an energy modeling wizard, some of the newer scenarios with VRF and heat pump are not great in that software. One of the great things, though, is it's free. Its development was in part paid for by the Department of Energy, and as such, it has to be free software. It's user-friendly. It has a user interface, which is nice. It also has components of it that help train workforce coming into the industry, because it can simplify things to help you investigate things on a high level. Then there's Energy Plus. Energy Plus has taken over the public funding from Equest, so it is another free software. It is much more detailed. Its development before going mainstream was done by those in research who are very detail-oriented. And as such, you can get very detailed with the energy model itself. And that's one of its strengths. It is really tough, though. It takes a lot of time to run the energy model. So Equest, if you're running 12,000 runs, that's you press go on the computer and it's like a day and a half. The computer just sits there and cranks through the calculations. If you're doing that same sort of scenario with Energy Plus, it's more detailed, and in its algorithms, it would take 5 days, maybe. Which then that's for a single computer, which isn't necessarily a big issue in our current cloud-based world, right? Instead of running it on one computer, you can parse it out to 100 servers and be done in an hour with all of that. So that is less of an issue potentially, unless you're looking at bottom line. It's overhead to make that happen, and the cost of doing business. Open Studio is a software that actually uses Energy Plus, but it actually trims down features that aren't typically used in Energy Plus, so it runs faster. And it adds a user interface, which is very, very nice. And it has a fairly large community that follows it. So there's feedback that's given to the development team. It continues to get better. The same for the Energy Plus as well. Other softwares, IESVE is the first paid-for software, really, that we could talk about. I think actually Open Studio started as a free software, but is now paid-for software. IESVE is a paid-for software. It does a lot of great things. It uses a lot of plugins to its software. So you can use its base software, or you can use plugins for natural ventilation, or plugins for daylighting, or plugins for what is called CFD, or computational fluid dynamics, which is very nice. Train Trace is actually used by a lot of mechanical engineers for sizing of mechanical equipment, but it has been used as well for energy modeling itself to give operational costs. It has recently upgraded its user interface to Trace 3D Plus, and I think last time I heard they're still kind of working out some kinks there. Design Builder is similar to Open Studio in some ways. I'm less familiar with that software, though. I don't want to misspeak, so we'll let you read that. And HAP is still used, but is a pretty small slice of the pie as far as industry standards are concerned. Feel free to go back and review those if you're really interested in them. Okay, so interpreting energy model results, there are things you want to look at. There's you can look at energy over the course of a year. You can also look at demand or peak instances when you might want to shave those peaks based on saving money. You can also compare based on what we talked about earlier, EUI. You can look at your carbon footprint over time. You can look at cost savings. Some challenges, I mentioned earlier, garbage in, garbage out. You need accurate data. If you don't have accurate data, it's not going to work. Interdisciplinary coordination, you're looking at your architect, your mechanical and electrical and plumbing engineers, and your owner group working closely to get the energy model put together. Then you have to maintain it. It's one more thing that you have to coordinate as design and changes progress. And then the compliance validation. It's because, although it's a growing trend, it's not a trend yet that's made it on people's radar. Compliance validation can be a struggle based on the expertise of the jurisdiction having authority. And then calibration, again, we talked about that as well. So I've got some case studies that I'd like to run through. They are local case studies. So let's jump into that. Who knows what building this is? No, it's not Utah Housing. I'm glad you don't know because I didn't put the name on the slides. I want it to be anonymous, but so I was curious if anybody knew what it was. Okay, so the project overview. This project is an existing building. It's in Salt Lake City, Utah. It's an office building, and it's about 80,000 square feet. If you were doing a renovation, what might you use the energy model for? An energy model for?
Window package will give you the best sort of bang for buck.
Holy moly. How did you know that? So, yeah, specifically on this project, the owner was potentially going to invest a significant amount of money in upgrading glazing. Oops, did I go too far? No, I didn't. Upwards of like $3.5 million. Because they wanted to look at what's called electrochromic glazing, which you can basically change the solar heat gain coefficient of the window's performance, which in real time, which is kind of cool, of electrochromic glazing. They put an extra film on it, and you shoot a little bit of electricity through it, and based on the amount of electricity you shoot through it, it gets darker. Not opaque. It goes to 99% opaque. It's not privacy glass though. Privacy glass is 100% opaque, right? This goes to 99%. Yeah. And so based on the results, this is kind of what the energy model spit out for them for a 40-year life cycle cost savings analysis. They were looking at several traditional glazing types, but then over here on the right, they have the electrochromic glass. Now you'll notice that the life cycle savings look pretty attractive over here. I mean, over 40 years, if they install this glass, they'll save a lot of money based on replacement costs and operational costs, maintenance costs, those sorts of things. But there's a catch down here with this red text, that the electrochromic glass packages were looking at offsetting their cost with IRA tax credit funds. The only reason why they penciled out was because of that. And the owner didn't like the risk associated with that, so they ended up not installing the electrochromic glass and going with more traditional package. So that's the outcome. And they actually went with the Azuria. So let's see, who knows this building? Yes, that's true. And I will let you know the picture is not actually taken on from the ground. This is a roof level, so it's even harder. Good, you don't know. I'm so glad I made my slides look better with pictures, but I still hid the actual building type. So that's okay. So this scenario again, Salt Lake City, it is a hospital, but it has many uses within it. Such as office, lobby, parking. There's a learning center, dining. There's a full-service kitchen. They have cadavers and autopsies. There's a penthouse. And it's about 190,000 square feet. What would you use an energy model for on this project? What's that? The atrium. The atrium? There actually is not an atrium in this project. That is not an atrium. Yeah, see how the architect was able to disguise that? Yeah. Yeah. Not an atrium. So, code compliance. Oh, I tricked you actually. So the data we're going to look at is actually from a different project. I don't have the rights to show a picture of the other project that this actually is, so I just threw a random picture of a hospital in there that I do have the rights to share. So this one was for code compliance, believe it or not. So the architect on this project said they wanted to use more than 30% window-to-wall ratio on the project. And the owner was like, that isn't gonna meet code requirements. And so the architect proposed to go with performance compliance so that they could put more glass on the building and have those trade-offs. Unfortunately, this was before P&L came up with that really detailed spreadsheet. And so the code reviewer was not super happy with what was submitted on this project. PDFs, such as this, were submitted that don't come with a checklist of mandatory measures or inspection requirements. And so in this case, the jurisdiction having authority was accepted this path to code compliance, which is a step that you should always verify before going down this road, is to make sure the jurisdiction having authority approves this path and has the expertise to do it. But they didn't like it on the back end when they actually got the documentation, and they were like, what am I supposed to do with this? There's no green bar. Like, what is my inspector going to take out to the site? Like, where are the check boxes? So that's why I'm glad that P&L found the funding to provide to come up with that spreadsheet, because this ended up being a very difficult process. The other thing is these spreadsheets the spreadsheet requires the professionals to sign off on the information. These didn't. So CompCheck, you usually see a stamp and a signature from the professionals. The jurisdiction having authority, they're like, hey, where's all the stamps? Why aren't they taking liability on for this? These forms did not require that. And these forms are made by ASHRAE, though they're not in use anymore. And ASHRAE said it's up to the jurisdiction having authority as to whether or not they require them to stamp. We're not going to put a stamp spot on these for them. So that was also really big. I'm glad we've moved past that. Again, the no green bar was an issue because the code reviewer was used to seeing that for CompCheck. So the third case study, new construction. This one's going to be LEED certified net zero. Does anybody recognize this building? By the background, what are you guessing? Yeah, that's good. That's true. This is a rendering, so the building hasn't been built yet. So if you recognize it, you are really good at what you do. But thanks for inferring the location. So it's Mountain Valley, Utah, right? Or I guess it's deducing, not inferring. It is a higher education building, and an energy model was used, even though it's small, 10,600 square feet, because it had other goals as well. And so the approach on this one, there was an EUI target requirement. LEED was involved. They wanted to right size the solar, and then there was the energy cost budget method was applied as well. But in this case, not for code compliance, but for the utility incentive. And so, yeah, both Rocky Mountain Power and Enbridge accept energy modeling results for utility incentives. So the outcome of that project was that, you know, the EUI compliance was confirmed, the right amount of lead points were achieved, and all parties received utility incentives and rebates, or qualified for them. We're almost done, actually. So I'm gonna speed up a little bit, back out again and review some of the trends that we're seeing, because that seemed to stimulate some conversation that we had earlier. So energy code national trends, there's a national and somewhat local trend to start reducing carbon emissions. There's been a shift in focusing on energy and cost, not necessarily a shift, I would say just an added layer, potentially, for reducing carbon emissions. There are different motivations for that. Sustainability is driving most of it. Let's see. Some trends are that, you know, we looked at the line graph early in the presentation about Iecc and 90.1. The trend is that both of those codes eventually get down to zero, or have a path to get down to the very bottom of that graph. And that eventually Iecc will end up catching up with 90.1, and they'll meet at some point. A lot of what's driving that is climate resilience. And there's a reason why I used those terms and not other more used terms, because it is resilience more than anything else, no matter where you are in the spectrum of climate. Other things are, there's an increased focus on indoor air quality. I hinted at this earlier. COVID is still working its way, the effects of COVID-19 are still working its way into the energy codes, with filtration requirements, whether those be actual filters or IR disinfectors in ductwork, that sort of thing. I know a lot of larger institutions have come up with their own standards in the interim, but that's going to make it into code in a more rigorous way. Keys for Utah specific are that because there are trends nationally moving towards this performance-based approach to energy code, there's an effort to train and educate professionals locally. And because of that, locally there will be a focus now not just on compliance, but on lower first costs, overall energy use reduction, which may also include the layer of carbon on it. And then I mentioned as well that renewable energy is kind of a new thing in the energy code that will continue to be refined in the energy code in upcoming iterations. And we expect as well that batteries will be added at some point as an option or a path. Either if, for example, if you have batteries on your project, you might qualify for an exception in some cases. But it's coming. When it comes to batteries, not based on energy, but other parts of the energy code, it is current recommendation to try and actually just place the batteries outside. They do have exterior grade batteries that can just sit on a sidewalk, and then you don't have to worry about fire rated barriers on the interior of the building. I think right now the codes don't differentiate between battery types. So if you have a lithium ion battery, you're required to put a 3-hour rated enclosure around it if it's in your building. If you have a saltwater based battery, you're required to put a 3-hour rated barrier around it if it's inside your building. Literally, the contents of the batteries are salt water. and you have to put a 3-hour barrier. So there are refinements that are going to happen as batteries enter into the building code and the energy code. There is a push towards net zero buildings in general, and net zero energy buildings as well. The definition of what a net zero energy building though is varies widely. I have an hour presentation just on the definition of what net zero energy is or could be, based on how to crunch the numbers and what your priorities are and what you want to highlight in your project or with your project. Let's see. I think we're going to have to bypass some of these. You'll all get a copy though of the presentation as well. I think it'll be posted online and potentially sent out. So other ways that technology may change energy code as tools become more integral and more widely used, they'll evolve and provide more deep insights into energy analysis. The Internet of Things is changing things. Artificial intelligence has already started to be included in building operations, where you get real-time feedback from the building, and artificial intelligence actually just fixes things for you or tells you what to fix for you and does all the thinking, which is pretty exciting and pretty scary all at once. And I think, did I already cover? Yeah, I did already cover it. That's a repeat slide. I apologize for that. We'll continue to see sustainability standards or certifications get more rigorous as energy codes also continue to get more stringent. We'll see the benefits of all of these things in our climate resilience and our adaptability. And as we prepare for the future, we need to educate our workforce. We need to keep up with codes as they are updated. And we need to be advocates as well. A lot of the way the energy codes are updated is by council and committee, not necessarily by the numbers. And so the more advocacy and involvement that we have, the better chance we have of them appropriately changing. So these are the things we've covered today. Oh, right there. And that's my contact information. Any questions? We covered a lot, but we stayed at a high level as well. I understand that. So if there are any detailed questions after the fact, I can dive into the details as much as you want.
I have a strange question. So there's energy compliant codes. Do you foresee there being energy compliance with users of energy?
There is a movement to look at that. I mentioned earlier in the presentation some unregulated portions of the energy code, and users or occupants of the building is one of those unregulated things. And there are companies out there, even local companies, who are looking at that. They have come up with systems that gamify building energy efficiency for occupants. So they engage occupants. You get points by doing certain actions, and then there's a prize at the end. Again, they started this study, they did R&D with this product with students. They found, interestingly enough, that if the prizes are too good, people cheat. And if the prizes aren't good enough, nobody cares. And so there's a balance there. And especially when they found that the cheating was mostly like people created bots to just go into the system is based on the honor system. And so they create bots that just go into the app forum and complete all the actions and say they've done everything, right? And so there's a balance there. They've refined it. I think the program, locally at least, is called Inhabit. So there are people looking at that. There are research institutions who are looking at that as well. that haven't really come to market yet. I think since they're more research-based, they're looking at the impacts on energy modeling and code and applying it there instead of in real-life applications like this one software that I mentioned. But it's up and coming as well. People don't like to be told what to do, and so I doubt that it, in any form, anytime soon, makes it into the energy code or is codified. But people are looking at it, if that answers your question. Other questions? All right. Well, I thank you very much for your time, and I look forward to our continuing this conversation offline.
Thank you, everyone, for coming today. Just a couple of announcements. December 3rd, we will be doing a field training. So if you haven't had an opportunity to